Hi, today we are looking at section 9.3, which deals with reciprocal and quotient identities. So this is the start of us utilizing a variety of trig identities to help us simplify questions, prove identities, and solve questions. So a trigonometric identity is a statement that relates different trig ratios together. Now, we have already actually talked about one set of identities, which is our reciprocal identity. So we talked about cosecant theta is equal to 1 over sine theta. Secant theta is 1 over cosine theta. Cotangent is 1 over tan theta. So those were known as our reciprocal identities because we are taking the reciprocal of sine, cos, and tan. We also have what are known as quotient identities. So you get these by dividing sine and cosine. If we're taking sine and dividing by cosine, we get tangent. If we take cosine and divide by sine, we get cotangent. And of course, for each of these, our denominator cannot equal 0 because we cannot divide by 0. So that's what we'll talk about verifying and proving an identity. So verifying and proving are two entirely different things. Verifying essentially means that we're putting a value in for our variable and seeing if one set of equation equals another set of equation. Now, usually we'll verify before attempting to prove, because if verification doesn't work, we can't prove. Because proving means that one side of our equation is exactly equal to the other side of the equation. So if we were to, for example, graph them, they'd overlap perfectly. So proving an identity, we use proven trigonometric identities to show the each side of the equation can be written the same. Now, just because you can verify something doesn't mean that you can prove it. If you verify something, it just means that the one side of equation equals the other side of equation at that exact value of your variable. So it could just mean that you have the function on one side of equation intersecting the function on the other side of equation at that exact variable. So, example, for each identity, verify it for 30 degrees, and then we're going to prove identity. So this first one is we have secant theta plus or times 1 plus cos theta equals 1 plus secant theta. So we are going to first verify. So that means we're going to put in 30 degrees everywhere we have the angle. So we've got secant of 30 degrees times 1 plus cos of 30 degrees equals 1 plus secant of 30 degrees. Now, when I enter this first side in my calculator, that gives me 2.1547. When I put this other side in, I get the same thing. So I have verified it. So for part 2, for proving it, we're actually going to use our identities that we just went over. So we've got secant theta times 1 plus cos theta equals 1 plus secant theta. Now, I find for proving identities, the easiest way to do it is to simplify things as much as we can. So as a result, I always start working on whichever side looks more complex. So this side, the left side in this case, has more terms, so I would consider it to be more complex. So first thing I'm going to do is the secant we just learned, or we already know, is 1 over cosine. So I would replace this with 1 over cosine of our angle times 1 plus cos of our angle equals 1 plus secant of our angle. So 1 over cos times 1 is 1 over cos. So we multiply that by that. Now we're going to multiply this by this. So that's going to give us plus cos theta over cos theta. And we'll leave this side the same for the time being. Okay, 1 over cos theta is secant. So we've got secant theta plus cos over cos is 1 equals 1 plus secant theta. So we have essentially the exact same thing on both sides of our equation. So we can say our identity is proven. Okay, so we'll do another example where we verify 30 degrees and then prove. So we've got 1 minus tan theta equals cotangent theta minus 1 over cotangent theta. So part 1 was verifying. So we've got 1 minus tan of 30 equals cotangent of 30 minus 1 over cotangent of 30. Now calculating the left side of our equation, I get 0.4226. And doing the right side of the equation, I get the same thing. So I have verified it. Now that we've verified, we will prove it. So we've got 1 minus tan theta equals cotangent theta minus 1 over cotangent theta. Now, in this case, it looks like my right side of the equation is more complex. So I'll start with it. So left side I'll leave alone for now. So I've got 1 minus tan theta equals cotangent we know is 1 over tan theta. So one of the things I often will do is change into our 3 basic trig functions. So I've got 1 over tan theta minus 1 over 1 over tan theta. Now I've got fractions nested inside a fraction, so I am most likely going to want to get rid of those. So I'm going to multiply by tan theta over tan theta. So that's going to give me 1 minus tan theta equals tan theta over tan theta minus tan theta over tan theta over tan theta. So that gives us 1 minus tan theta equals tan theta over tan theta is 1 minus tan theta. Tan theta over tan theta is 1. So we can get rid of this denominator. So we've got 1 minus tan theta equals 1 minus tan theta. So we can say this identity is proven. Since we ended up with the same thing on both sides. Now we'll also have to often state our restrictions. For example, for each identity, determine the non-permissible values of theta and then prove the identity. So for this, I usually change it into our 3 basic trig ratios, sine, cos, and tan, and then come up with our restrictions. So cotangent is cos theta over sine theta. Cosecant is 1 over sine theta. And now we're going to look for restrictions. Now, this entire denominator will never equal 0 because we have 1 divided by anything is never 0. However, in this fraction and this fraction, we both have sine theta as a denominator. So we know that sine theta cannot equal 0. Now, we know from our graph of sine theta which we'll just quickly review. So our graph of sine theta looks something like this, where we have zeros at 0, pi, 2 pi, 3 pi, and so on. So therefore, theta cannot equal k times pi, where k is an integer. Now that we've done that, we'll prove identity. Now we have a fraction divided by a fraction. So if that's the same as multiplying by the reciprocal of this fraction down here. So that's times sine theta over 1. So that cancels with that. So that gives us cos theta equals cos theta. So we have proven this identity. Next one, we've got cos theta is equal to 1 plus cos theta over 1 plus secant theta. So once again, I will get this in terms of cosine and tan, and then come up with restrictions, and then we'll simplify. So we've got cos theta is equal to 1 plus cos theta over 1 plus 1 over cos theta. So this fraction, we know cos theta cannot equal 0. Now, if we recall our graph of cosine theta, we know that it starts at maximum. Its first 0 is at pi over 2, and then these are repeating every pi. So therefore, theta cannot equal pi over 2 plus pi times k, where once again, k is any integer. Now, the other thing with this is cos cannot equal -1. Because if cos equals -1, this term becomes -1, and we have 1 minus -1, which gives us 0. So cos is at -1 at pi, and then that repeats every 2 pi. So theta cannot equal pi plus 2 pi k, or once again, k is any integer. Okay, so now we'll go through and simplify this. So in this case, we once again have a fraction within a fraction, so we are going to want to get rid of that. So I'm going to multiply by cos theta over cos theta. Now, if I didn't have any fractions in my numerator, I will usually not bother multiplying out the numerator. I'll just put cos theta in brackets, multiplying by what was already there, so 1 plus cos theta, because often we'll end up with things canceling out if we don't FOIL out our numerator. So we've got cos theta times 1 is cos theta, and then cos theta over cos theta. So simplifying this a bit, we've got cos theta is equal to cos theta times 1 plus cos theta all over cos theta plus 1. Now, 1 plus cos theta is the exact same thing as cos theta plus 1, so that cancels with that. So that gives us cos theta equals cos theta. So we can say identity proven. Okay, so next we'll look at solving utilizing our identities. So sometimes we'll have to use our trigonometric identities to solve for a variable. So, for example, use algebra to solve over the domain from 0 to 2 pi. And we've got 2 sine x equals 3 plus 2 cosecant x. Now, whenever we are solving, we typically want to have in sine, cos, and tan, because we're able to use those in our calculator. We're also familiar with them with special triangles. So as I expand this out, I've got 2 sine of x equals 3 plus 2. I'm going to change this in terms of sine, cos, and tan. So cosecant x is 1 over sine x. Now, if we're solving, having this as a fraction isn't very helpful, so I'm going to multiply both sides of the equation by sine x. So multiplying by sine x gives us 2 sine squared x equals 3 sine x. And then here, our sine x's cancel out, so we just get 2. So we can see we have a quadratic equation with our sine x. So we'll move this stuff to this side. So that gives us 2 sine squared x minus 3 sine x minus 2 equals 0. Now for factoring these, I find it's often easier to temporarily get rid of the signs. So I'll just say, for example, sine x is equal to m. So if I rewrite this with m's, for anywhere we have sine x, we've got 2m squared minus 3m minus 2. We want to product sum factor that. So we have a product of 2 times -2, so -4 with a sum of -3. We'll start each of our brackets with 2m. And then two things that multiply to -4, add to -3, it'd be -4, +1. We'll divide our extra factor of 2 out of this one. So that gives us m minus 2 times 2m plus 1. So what we'll do is we'll write that back here, and we'll substitute sine x back in for m. So we've got sine x minus 2 times 2 sine x plus 1. And we know that equals 0. Now, we need to find what value of x makes each of these brackets equal to 0. So we can take each of them and create our own equation of them. So we've got sine x minus 2 equals 0, because if this term equals 0, 0 times anything is 0. And same thing with this one. So 2 sine of x plus 1 equals 0. Now this one will move the 2 to the other side. So we've got sine x equals 2. Now this one has no solution. We know that because we don't have an amplitude in front of here, and our graph of sine x oscillates between +1 and -1, so it never equals 2. So now we'll look at this side. So we'll move 1 to the other side. So we've got 2 sine x equals -1. We've got this 2 to move over, so we divide by 2. So we've got sine x equals -1/2. Now, based off of that, we know that sine is negative down here and down here. Now, sine is opposite over hypotenuse, so we know this is -1, this is 2. We should recognize this as a special triangle, so this is √3, which means this is pi/6. Which also means this one's pi/6 as well. Now, trying to get our total angles, we're going between 0 and 2 pi. So going from here to here would be pi plus pi/6. So one of our answers is 7 pi/6. And then the other one, we're going from here all the way to here. So we're almost 2 pi, but we're short by pi/6. So where you have 2 pi minus pi/6. So that would be 11 pi/6. Okay, so that gives us x is equal to 7 pi/6 and 11 pi/6. Now, in this unit, if you had plugged this in your calculator, you would not get full marks because it utilizes special triangles. So we want exact answers. So to get full marks, you would need to have your 7 pi/6 and 11 pi/6 and show that you're getting them here and not just guessing from a decimal that you got with your calculator. Okay, so last example, we've got sine x equals cos x. And we're once again going from 0 to 2 pi. Now, there's a variety of things we could do. One is we could subtract sine x from both sides or cos x from both sides, but that doesn't match any of the identities we have. Now, if we do division to move one of these to the other side, we can end up with our tangent x or cotangent x. Now, it's more advisable to go to the one that is a basic trig function, so tan x. So I would probably divide both sides by cos x. So sine x over cos x is tan x, and cos x divided by cos x is 1. Now we have tan x equals 1. Tan we know is positive here and here. Now, if tan equals 1, that means our opposite and adjacent are the same length. Which means it's a 45-degree triangle, which you should know that in radians is pi over 4. Now, this one answer is in quadrant 1, so it's going to stay as pi over 4. This one here, we go pi plus pi over 4, which gives us 5 pi over 4. And those are our two answers.